I'm going to stay around after class again today to talk to anybody who wants to have any questions about the final and all that. But we'll talk about the final again on that last class when we have the cookies and the movie and my shirt, so to speak. So, Cox model, the extended Cox model, we talked about these different kinds of variables, different kinds of time-dependent variables. And the two basic kinds are what are called defined time-dependent variables, which is usually of the form involving a time-independent variable times some function of time, which could be just time itself or could be some weirder looking function like the log of t minus 3. You might have a minus 3 in there if you're interested in sort of considering lag time. I mentioned something about that, and that's a defined time-dependent variable, and the reason why it's called defined is because the time-independent variable, part of this definition or part of this kind of variable, once you know that, then the rest of the variable can be completely determined, because if you know that the person's male, then you know every value that this variable can take. Whereas an internal or ancillary time-dependent variable is a variable where you don't know what the values are going to be. They could be different for different people. For a given person, their exposure status may change over time, and you're not sure what it is for a different person. It depends upon what their experience is, what their own internal or ancillary experience is. And I also mentioned something called the Heaviside function, which we'll get to look at today in terms of how it works. What it looks. I mentioned something about Dr. Heaviside, who's spelled with an I, not a Y, and all that. So we looked at what the model looked like, and this is what the extended Cox model looks like, and basically it's a hazard function form of the model, the way to define the model, and it involves two kinds of predictive variables. It involves time-independent variables and also time-dependent variables. And if you don't have any time-dependent variables, just have time-independent variables, then you have the Cox proportional hazards model. Once you're adding these kinds of variables, you're talking about a model that's an extended Cox model that deals with time-dependent variables. And we talked about what this model looks like. One thing I didn't say that I'm going to say a little bit later, but I might as well say it right now, is that if you're using an extended Cox model and you're using SAS to estimate the parameters in the model and to get hazard ratios and to test hypotheses like you do for any survival or even logistic regression model using maximum likelihood estimation, but if it's an extended Cox model, it turns out that SAS, proc-pH-reg, and most other packages will not allow you to plot survivor curves. Even though there is a formula, as you know, that we mentioned, the formula that relates a hazard function to a survivor curve. But typically, you're not going to be able to plot survivor curves because these computer programs won't allow you to do it. And the main reason why it doesn't allow you to plot these things is because it doesn't really know what to plot. I mean, if you have one person whose values of the exposure variables changing from one time to another, and you have another person whose exposure values are changing from one, but maybe differently than the first person, how does the computer know what to plot? Because it doesn't have a fixed set of exposure variables to plot. So what typically happens is it doesn't let you plot it. Now, there is a way that you can plot survivor curves in certain situations, but it's not in any of the packages as far as the standard packages that people use other than SAS. I mean, there's Stata and there's SPSS and there's even R. I don't think it's in any of those packages. There's a longtime friend of mine who's from Australia who wrote a package that's added something in there where you can actually plot survivor curves. But anyhow, that's all I want to say. You can't plot survivor curves if you want to fit an extended Cox model. That maybe actually says something if you have a choice between an extended Cox model and a stratified Cox model. we know you can plot survivor curves for a stratified Cox model. So that may be one reason to choose a stratified Cox model instead of an extended Cox model, just if you want to get survivor curves. We'll see an example of this shortly. But in any case, you know, the way this thing is fit is maximum likelihood estimation, and I talked about how the key characteristic is that the hazard function, the value of the hazard function depends upon the value of the variables at the particular time, and not at an earlier time or a later time, but you could consider lag times if you wanted to allow for an earlier time to have an effect on a hazard at a later time. And then I mentioned also that if you talk about the hazard ratio from this model, the hazard ratio technically, when you get the hazard of for one person divided by the hazard for another person, you get an expression for the hazard ratio that is not independent of time. So that's why the extended Cox model is got a different name, is because it's not a proportional hazards model. In theory, it doesn't depend upon time. Although there are situations, as I mentioned briefly last time, there are situations in practice where the hazard ratio may actually be independent of time. And I showed you an example of that where I showed you a couple of examples, but one of the examples I showed you is where very simple example where the only variable in the model is a time-dependent variable of exposure status, which changes over time. And if this was your model, the hazard function is the baseline hazard times e to the delta E of t, where E of t is a time-dependent variable, then the hazard ratio formula is going to give you an expression that doesn't involve time, because the coefficient of this variable doesn't involve time. So what does it mean? What does the hazard ratio mean if you're talking about an exposure variable that's time-dependent? Or another way of saying is, does it mean the same thing as if you were dealing with an exposure variable that wasn't time dependent? In other words, what if you had an exposure variable, you're either exposed or unexposed, and you fit a model where you didn't have E of t, you just had E, it's either 0 or 1. Well, in that case, the formula for the hazard ratio is e to the beta, or e to the coefficient of the exposure variable. In this case, it's also e to the beta, although I've called it a delta. Will e to the beta in a model that has a time-independent variable for an exposure does it mean the same thing as e to the beta for a model where you have a time-dependent variable? It doesn't mean the same thing, because in one case you're just comparing two groups. You're either exposed or unexposed, either in one group or the other group. But if you're talking about a time-dependent variable, you're not talking about a person who's always exposed or always unexposed. They're changing around. So you can't interpret in this case, e to the delta, the same way you interpret as if E was a time-independent variable. It actually represents some overall effect of exposure, considering the fact that people's exposure status, a given person's exposure, is changing over time. So it has a little trickier interpretation. We'll see more of this with some of the examples that we deal with. But anyhow, now the last thing I wanted to do that I didn't get to do was to show you how you actually set up the computer to deal with a model where you have a time-dependent variable. So in this particular case, I'm just going to show you how you would create a time-dependent predictive variable that measures blood pressure, where you've got a bunch of people in your study where you've measured blood pressure at several times. So for each person in the study, the blood pressure is measured more than once. So if you want to consider a model where you've got a variable that's blood pressure that's changing over time, and that's the variable you want to put in the model, how do you set it up? Now, how do you set up the code for that? And in this case, the outcome variable is survival time. The censoring variable is whether or not somebody was censored or not, or failed. And then I've got blood pressure values there was an initial blood pressure, and then there was possibly another blood pressure taken later at time t1, and possibly another blood pressure taken at time t2. So here's some data here. Now I'm clicking to the next slide. Here's some data. okay? And basically I have 10 people. I'm looking at this picture. I have 10 people, okay? And now you see where it says time 20 and sensor 1. So what does time 20 mean? What's the time variable? This is person 1, observation 1, and their survival time was 20, whatever it was, 20 days, let's say, or 20 weeks, say. Okay. And the second person's survival time was 34 weeks. Third person's survival time was 12 weeks. Okay. Now this first person gets a value 1 for sensor. So what does that mean? They failed. Whatever the outcome is. If the outcome is death, they died, or they got whatever the illness was. Okay. Or they went out of remission, or whatever it is. So the third person was censored, and the fourth person failed, and so on. Okay, so what about BP0? What does this 88 mean? What do you think we're talking about? Systolic or diastolic? Well, I'm not sure. Let's assume it's systolic. Let's assume it's diastolic, because it's lower. Okay, assume it's diastolic. So 88, what does that mean? So on person 1, their initial blood pressure at the start, when you first looked at them, was 88. That's their blood pressure reading, their diastolic blood pressure. Okay, at time 15, their blood pressure changed to 92. Went from 88, and then 15 weeks later, it changed to 92. Okay, and then 25 weeks after they were initially looked at, it changed to 75. Okay, that's the first person. Second person started at 95, changed to 110, and then changed again to 99. So now, notice that this first person, their survival time was 20. Okay, so let's assume that the outcome is not death. Why does it make sense to assume that the outcome is not death in this case? Because I have a blood pressure at 25. So, this is not meant to be funny, but it wouldn't make sense to have a blood pressure at time 25. So let's assume it's some illness or something, okay? So what are we talking about for that person? What are we talking about how their blood pressure has changed? Well, it started at 88, and at time 15, it changed to 92, and then at time 25, which you never got to. You never got to time 25. So what happens with this person? So what does it make sense to assume here? You assume that it starts at 88, and it's the blood pressure, so you don't have any other measurement of blood pressure until 15 weeks. It's 88 up until 15 weeks. And then at 15 weeks, it changes, because that's the next time you have a blood pressure. It changes to 92. And at 20 weeks, it's still 92. Right? Because it hasn't gotten to 25 weeks. So that person, up until the time they failed, had an 88, then it changed to a 92, and that's it, as far as you have on that person. What about the second person, whose survival time is 34? Well, they started with 95. At 12 weeks, they changed to 110. What about at 30 weeks? Did they change? Well, their survival time is 34, so they did change at 30 weeks. So it does go from 95 to 110 to 99. So how do you tell the computer that you want to consider a person 1, person 2, whose blood pressure values are changing over time? How do you tell the computer to define that variable? Well, here's the code for it. Well, first of all, I've put in the information that's in this table. Defining the data set, blood pressure dependent, time dependent, and then the variables are observation time, sensor, that's the sensor variable, and then I've got these other variables, blood pressure's time 0, time 1, so on, and here's the data, okay, and now I say proc print run, so I can show what the data looks like, and then here it is, proc pH reg, model time star sensor 0, equals BP. So what have I done here? What have I done? I'm using a model. What's the outcome variable? Time. That's the outcome variable. What's the censoring variable? A variable I've called sensor. What's the value of the censoring variable if somebody is censored? 0. And how many variables are in this model? How many variables are one? And what's the name of the variable? BP, that's the name of the variable, okay? But however, up to this point, all I've done is put in the data and I've named this variable, but I haven't really told the program what to do with the data that I have in order to define a time-dependent variable. So what I do is I say, okay, this is what I do. The way it works, and I think they talked about this, but they didn't do it through this example in the lab yesterday. What you do is you say, okay, at time 0 for any person, the value of the BP variable is whatever that person's initial value was, which is BP 0. That's what it says. Okay. Then it says, if the survival time is greater than T1, if somebody survives at least as large as, like for person 1, it's 15. Person survives past 15 and it's not missing, then the blood pressure changes at after time T1 to the next blood pressure value, which is 92. Okay. If time is greater than T2, time in this case, once it gets past 25, you're not going to have a BP value for the first person. So this is the way you're defining this variable. You're saying the person's value is changing from one time to the next up to the time that at least you were able to follow them until they were either failed or were censored. And that's what you do here. Now, the key thing about this, and I think this was said in the lab, is these statements about what's going on and how you're defining it are all being made after the model statement. After the model statement. If you wrote this and then you put the data in there, and if you wrote something like these statements before you said proc pH reg, if you wrote it while you were defining the data, or you've identified what the variables are, and you define these statements earlier, sort of in what's sometimes called the data step, it won't work. So when you're defining time-dependent variables, you have to do it after the model statement, not before the model statement. Now, this is something that you're going to get some experience on in the take-home final, because you're going to be asked to do some kind of time-dependent variable. And if you define it before the model statement, you're going to get incorrect answers. So it's a very important point that I'm making. Okay. So anyhow, that's what this does. And when you actually do it, you get this output, and then you wind up getting, now notice at the bottom of the screen, what do you see at the bottom of the screen? It says analysis of maximum likelihood estimates. How many variables do you see come out from this model? One, because you're fitting a model with only one variable. And it's a time-dependent variable because you've defined it that way according to the rules that you've specified after the model statement. So what you get for this particular variable is you get the variables, 1 degree of freedom, because it's just one variable, and you're getting an estimate, a standard error, a chi-square, a p-value, and a hazard ratio. So what's the 1.066? What is that? How is that computed? How is that computed? It's e to the what? E to the 0.06428. Okay. Now you notice it's close to 1, which essentially sort of, and it's not significant, as you can see. Well, not significant at the 5% level. So it suggests that there's no effect. Okay. No effect in what sense? Remember, you've got a different kind of variable. You don't have people who are either high or low throughout the whole time that you're following them. They're changing. Their blood pressure is changing. So what you're saying is, given that you've got a data set where individuals are changing their blood pressure over time, what's the overall effect of whether blood pressure, allowing it to change over time, has an effect on whether somebody survives or not? What's the overall effect? That's what you're getting. So you're not getting something comparing exposed with unexposed, or high blood pressure with low blood pressure. You're looking at an overall effect. So that's what this means. Now, with that, I now want to talk about, so that's just illustrating. All I'm trying to do here is illustrate how you code, how you use the computer, and the key message here is you use the computer, use pH reg by defining what's going on with this variable after the model statement. So with that, I'm now going to skip to an example. I want to skip to an example. And the example I'm going to talk about is something from, let's see if I can find it, this one. The Attucks Dataset. The Attucks Dataset. So I want to talk about the Attucks Dataset. So you have to find that part in your notes, okay? Then you find it. Is it there? There somewhere. So you have to, if you've copied it or printed it out, just find your page or look at the computer. Okay? This is an interesting data set in some ways because what the people that are being studied are heroin addicts. Okay? This was a study that was done in Australia. It's a 1991 Australian study of heroin addicts. Okay? This is a real data set. Okay? And the person who did this study, John Kaplan-Meier, there were other people involved. John Kaplan-Meier is actually a really good friend of mine because I actually took 2 years off way back when around 1990, 1989, and I lived in Australia. I lived in Sydney, Australia. I lived right near the beach in Australia. It was nice, okay? And John Kaplan-Meier became a very good friend of mine. He is the Crocodile Dundee of epidemiology. Believe it or not. He was quite a guy and he still is. I mean, I haven't seen him for a while, but he's also a big sports fan. We talk baseball and basketball and football and stuff like that by email, usually, you know. But in fact, we even watched the Super Bowl game together in Sydney, Australia in 1990 or something. But anyhow, he's an interesting guy. And he did the study was the main author of the study. And what it involved was, let's see if I have how many people. It was a study, can't remember how many people. Must be in the next, must be somewhere here, how many people. I don't know, don't remember somehow. But anyhow, the idea was everybody in the study was an addict, okay? And the key issue was how they're treated, how their addiction is being treated. And what was being compared was two different kinds of methadone clinics for treating their addiction, okay, which had different ways of relating to the patients. One clinic maybe was stricter than the other clinic in terms of how the people were allowed to live or how, you know, what the curfew was or whether they could go out of the clinic for a certain number of hours. And I don't know, I'm not sure. There were different characteristics of the two clinics. And the question was, does one clinic do better than the other in doing a better job of keeping them under care? So the time variable was the number of days remaining in treatment. Okay, and if they dropped out of the clinic, then they failed. Now that may seem a little weird because you might think if they dropped out of the clinic, they were cured, right? But the time of the study wasn't long enough for them to get cured. So the idea is you wanted to keep them in the clinic as long as possible so they could undergo the treatment and maybe get better that way. So if somebody dropped out early, that meant that something happened and they didn't do well, and they failed as far as, you know, staying under treatment, something like that. So the clinics had different treatment policies, different ways that they treated people. So the question is, which clinic did better? So that's the main. So the exposure variable is clinic. You know, which clinic has people that stay in the clinic longer? The ones that stay in there longer are doing better. They're surviving longer. That's the idea, okay? And there were two clinics, Clinic 1 and Clinic 2, okay? And that's our exposure variable, okay? The outcome variable is survival time in days in terms of how long they stayed in the clinic. The status variable is if they departed the clinic, they failed. That's what I'm saying, okay? Now, there were several variables that they were considering in addition to the main variable of interest, which is clinic. The clinic had two policies. Which clinic kept people in there longer, okay? One variable was whether the person in the clinic had a prison record or not. You might think that if they had a prison record, depending on what kind of record or whether they had a record at all, any or none, then somebody might have, a given person who had a record might not stay in there longer for some reason because they're a little bit more unstable. I'm not sure what the right way to say it, but they might have dropped out earlier. So that was one of the covariates, one of the potential confounders that was interested in being controlled for. And another one was what their methadone dose was. What kind of a dose were they getting? What was their maximum methadone dose? If somebody got a low dose, maybe they didn't stay in the clinic longer than if they got a high dose, what their maximum dose. So those were two of several variables, but I'm only going to talk about the analysis with regard to these two variables. Okay, so you got the question, you got the situation. Okay, now here's what happens. Okay, so first of all, here's a model. Okay, and you notice this model is what kind of a model? What kind of a model? Is it a Cox proportional hazards model, a stratified Cox model, an extended Cox model? What is it? It's a proportional hazards model because all the variables in the model are time-independent variables, right? So it's not an extended Cox model, okay? And it's not a stratified Cox, so you don't see a G here, right? So I'm putting all these variables in the model, okay? Now the question is, can I do that, okay? And what do you have to do to check that? Well, you have to check the proportional hazard assumption for these variables. Now, the three variables of interest here are all by themselves time-independent variables, okay? That doesn't mean you still may want to consider it an extended Cox model if it turns out the proportional hazard assumption isn't satisfied. You follow me on this thing? Okay, so now what I'm showing you here is, you see the last column, it says PPH? What do you think that means? PPH. P stands for p-value, and pH stands for proportional hazards. That's actually the p-value that you would get if you did what we call the goodness of fit test, that test that involves Schoenfeld residuals. That's the p-value that you get if you put all three variables, which again, you might want to do them independently before you put all three of them in there. But if you put all three in there, you get these three p-values for these three variables. What do you notice? What do you notice? Well, one of them's circled. That's what you notice, obviously. And it's circled because it's got 0.000, 3 decimal places. What does that suggest? Well, of the three variables, if there's any one that doesn't work, doesn't satisfy the assumption, it's the clinic variable, right? And it looks like the other two maybe are okay. Now, you might want to do more with this. You might want to leave the clinic variable out, put the prison and dose variable in there, and see if the clinic variable is still bad, just like we did with the sex variable when we're doing the remission time. But in any case, it looks like that from this, just from looking at this, that the clinic variable isn't satisfying the assumption. Now, in fact, if you actually fit a model, in fact, if you fit here's what happens when I plot the Kaplan-Meier curves comparing the two clinics. I think these are the Kaplan-Meier curves. Is that what it says? I'm going to look at this. Survival, distribution, function. Okay, so it's the Kaplan-Meier curves comparing Clinic 1 to Clinic 2. Okay, now what you notice about Clinic 1 and Clinic 2 is, if you're looking at these Kaplan-Meier curves, do you compare them to see if they're parallel, to see if the proportional hazard assumption is satisfied? And the answer is, that's not how you do it. What do you have to do? Log. There's the log curves. Okay. Now, if you look at these log curves, you would say, well, okay, these are comparing just the two. It's not dealing with any other variables. Does the clinic variable on its own seem to satisfy the assumption? Well, so many answers are it depends. In this case, you could say, well, no, because these two lines, they intersect over here, and they're almost the same over here, and they're somewhat different here. So it looks like you could say, no, these two curves are log curves are very different. The clinic variable as far as log curves doesn't satisfy the assumption. On the other hand, you might say, well, they're essentially the same here, and even though they're different, they're not that much different. Maybe they're really the same curve. If I wanted to see if they were the same curve, what might I do? if I did it. I didn't do it there. What might I do if I wanted to see if these two log-log curves or the corresponding survival curves are really estimating the same curve? Doesn't look like it when you look at the survival curves. But what would you do? You remember you learned one thing that you could do. Early on, we started talking about you would do a log rank test, right? Log rank test allows you to test for whether there's a significant difference in the two curves. If you did a log rank test and you found that it was significant, you would say, well, even though these things look like maybe they're the same curve, I've got some evidence that maybe they're significantly different from one another. And they look like they're intersecting at some point. They don't look parallel. So I have evidence from the graphical way of looking at the proportional hazard assumption, and I also have evidence from the PPH, or the goodness of fit test, that the clinic variable doesn't satisfy the assumption. I haven't really shown you the other variables other than the goodness of fit test for the other two variables. But it looks like from even the two things I saw, and you might want to do more complicated ways of looking at all this, and you're going to get a chance to do that type of thing on the take-home final, but it looks like the clinic variable doesn't satisfy the assumption. So I'm going to sort of say, let's assume it didn't, and that's what they concluded after they did a whole bunch of different things. So if the clinic variable doesn't satisfy the proportional hazard assumption, you got a problem. What's the problem? You know, if a variable doesn't satisfy the assumption, what's the first thing you think about doing, about dealing with it? Stratify on it, right? If you stratify on the clinic variable, I already talked about this when I started talking about stratified Cox. If you stratify on the clinic variable, you're not putting it in the model. So if you don't put the clinic variable in the model, how are you going to get a hazard ratio for the effective clinic? You can't go e to the beta. Beta is the coefficient of the clinic variable because it's not in the model. Okay? So you got a problem that you can't really solve by putting it in a stratified, leaving it out of a stratified Cox model that has prison and dose in there, but leaves out clinic. So another option, an alternative option you have is to say, well, look, I can't do a stratified Cox model. I have to do something else. I can leave clinic in the model, but now I'm going to put in time-dependent variable to try to allow myself to even test for the effective clinic. That's what you do, in particular when you got a variable in this situation which doesn't satisfy, and it's your exposure variable. So this is sort of an interesting example just from that point of view. So let's see. Now, what did I do here? Well, I'm using Kaplan-Meier plots and log-log plots. And now let me just look at this. Now, if you look at this, even though these aren't log-log plots, they're survival plots. What do you know? And these are Kaplan-Meier survival plots. Okay. What do you notice about this in terms of looking at what's going on between the two clinics? I mean, if you looked at these, you haven't control for the other variables. You're just looking at these survival plots. What does it seem to suggest? Does one clinic do better than the other clinic? And it looks like, yeah, it's always doing better. But is it always doing better to the same extent? And the answer is no, not necessarily, because early on, what's going on? Early on, this clinic, which is, I don't know, this is clinic B, whichever one it is. I'm not sure the difference between the two characteristics of the clinics. There are different restrictions or something. But clinic B is always better, but it's early on, it's always a little bit better than clinic A, but later it's a lot better, right? What does that suggest? What does that suggest? If it's a little bit better early and a lot better later, and you're thinking about how you measure the effect of exposure, what does that suggest? Think about that. What does it suggest? It says early on, the hazard ratio that compares one hazard of one clinic with the other clinic, hazard ratio, is going to be smaller early on than it's going to be later, right? Hazard isn't that what it suggests? Okay. If the hazard ratio is smaller earlier and bigger later, what does that mean about a proportional hazard assumption? Comparing the two clinics. Well, it's not satisfied, just like I've already, because the hazard ratio early on is a lot smaller than it is later. So the hazard ratio isn't constant over time, it changes. Early on it's smaller than it is later. Okay, now another thing, now there are a lot of different ways you can look at it. You could say early on it's smaller, but not that much different. And later on it's larger. And it's true that these curves diverge, but you could say, well, maybe considering random error or something like that, maybe early on it's smaller but a certain constant, the hazard ratio, and later on it's also different than earlier on, but it's a sort of constant, the ratio is constant. That may be questionable. But if you had that, you're talking about considering a model, an extended Cox model that considers what's called a Heaviside function. Because you're allowing you to consider something that says the hazard ratio is constant before a certain time point and it's constant afterwards, but it's not the same. Okay, we'll look at how you do this in a minute here. But let me just go on a little bit further, even with this example. Where does it look like things change? If you wanted to see at what point, you look at the picture and you want to get some kind of an idea of when, it's close early and it's late, it's further apart later. Where does it look like things change? Well, what would you do? You look at the graph and you'd say, okay, well, it's somewhere, it's just rough here. Somewhere around here. Then you'd go to the time. What do you get when you go to the time? What do you get? When I go down here and I go down here, and this is days, what do I get? I get something that's close to a year. I mean, I'm just getting a rough estimate. In other words, it looks like up to a year, there's not much of a difference, but there is a difference. And after a year, there's a bigger difference. So if I wanted to do something to define a model where the hazard ratio is constant below a certain time and a different constant after a certain time, maybe a good cut point is a year, because that's what the graph says. And this would tell me how to do the analysis. So that's why this is sort of as good an example as you can get on how to consider doing the analysis. Because you look at this thing and say, well, it looks like there's, we've already checked things about the proportional hazard assumption. It doesn't look like it's satisfied. And now we can see, well, maybe the hazard ratio is different after or before a year and after a year. Maybe we could do something with that in terms of our extended Cox model, how we're going to define it. So that's what I'm saying. Okay. Now, it turns out, by the way, remember I said do the log rank test? When I do the log rank test, what happens? Highly significant. So this picture, which compares these two log-log curves or the two survivor curves, says they're significantly different. So it looks like I could argue that I do have different curves, and it looks like the proportional hazard assumption isn't satisfied for clinic. So we're going through an example here, okay? And this is, I think you can understand this thing, and it's survival analysis, and it looks like we're in trouble in the sense that we can't necessarily stratify on this variable, because if we do, we can't get a hazard ratio for it. So what do? Well, the first thing we might do is we might say, well, let's do it anyhow. Let's stratify on clinic anyhow, even though if I do it, I can't get a hazard ratio. So I run the model and I do something where I plot things and I go, let's see, where did I write anything about proc means? This is more computer stuff. And eventually over here, you see where it says model, days, star status, prison dose, and then it says straight a clinic. See that? So what I've done is I've done something, I maybe don't really want to do. I'm stratifying on the clinic variable. I'm putting prison and dose in the model. Okay. And when I do that, and I'm getting some plots, okay? And when I do that, this is what I get. These are the adjusted survivor curves. This is a sketch of the adjusted survivor curve. I actually think I have the plot. I actually have a plot of the sketch, but this is the sketch, and this sort of looks like this, but the time axis is a little different. But that's what you get for the adjusted survivor curves. When I compare Clinic 2 and Clinic 1. And I've adjusted I put the two variables in the model, okay? So now, does this tell me something? Does this tell me something about comparing how the two clinics do? Well, I don't get a hazard ratio, right? But I certainly do get a picture of what's going on over time. And it certainly looks like that Clinic 2 is doing better than Clinic 1 in the same way it did when I didn't adjust for anything. when I didn't put anything in the model, I'm getting almost the same picture here. Now I've adjusted for the variables. But I can't get a hazard ratio because I don't have clinic in the model. But I can get an analysis. I can get some information about what's going on. So it doesn't automatically mean just because a variable doesn't satisfy the proportional hazards assumption, you can't stratify on it and still get some meaningful information. I'm doing it, and I'm getting two survivor curves that don't allow me to get a hazard ratio, but at least it tells me something about how the two clinics are comparing. So that's the stratified Cox approach. What about, and that's the stratified Cox output, but let's look at this. This is the thing I wanted. This is an extended Cox model. Look at this model. Now, this is the thing we're going to look at now. Okay? This is an extended Cox model. Can you tell it's an extended Cox model? How can you tell it's an extended Cox model? Well, you have to look at the variables that are in the model, the predictive variables. One of them is clinic, a time-independent variable. Another one is prison status, whether they had any prison record or not. Another is dose, the maximum methadone dose, which is a continuous variable. Okay, and then there's this variable. What is this variable? Clinic times something called G of T. Okay. Now, can you tell from what I've written over here, that what kind of a variable is this? It's a time-dependent variable. Why? However I've defined G of T, it's a time-independent variable times some function of time. And I define the function here. But that's what it is. It's a function of time. What kind of time-dependent variable is it? A defined or an internal? It's a defined because it's a product of a time-independent variable times some function of time. Okay? And here's the function of time. G of T is 1 if T is greater than or equal to 365 days, and 0 if T is less than 365. Why did I choose 365? Because I showed you it on the graph. You know, that's the logic. That was a sort of a guess point. I could have taken 363, but maybe I could do a sensitivity analysis and try 363. I could try some other things, but it made sense to pick something like that. It's about 1 year. So, and then I've got this variable clinic, which is one, and now I'm actually changing the coding of clinic. Previously clinic was 1 or 2, but now I'm trying to make it a 0-1 variable because, and this is something you should do in most of your studies, if you have a variable that has 2 categories, and it's coded differently from 0-1, you might get into trouble if you leave it that way and you've got all sorts of product terms in the model. You might have trouble trying to interpret what the thing means. So it's always good to change it to a 0-1 variable, which is what I did. I changed it 1 of clinic 1, 0 of clinic 2, even though clinic 2 was originally 2. Okay. Now, look at what I got there at the bottom of the screen. See what it says? T greater than the 365, and I tell you what the hazard ratio is. Can you figure that out based on what you see on the screen? Can you figure that out? So let's say, suppose T is greater than or equal to 365. Now, this is simple to explain, okay? What's the value of G of T? T is greater than 365. 1, right? What's the value of this product term when T is greater than or equal to 365? It's clinic times 1, right? Isn't it? Clinic times 1. So what's the model look like when T is greater than 365? It's got beta 2 times clinic. There were some other variables here, so I'm only talking about the notation for these betas are different than 1, 2, 3, 4. Beta 2 is the coefficient of clinic, beta 5 times prison, beta 6 times, and what is this? Delta times clinic times 1, right? Which is delta times clinic, right? You notice that clinic is in there twice when G of T is 1, right? So you can actually say, you can rewrite this thing by writing it as e to the beta 2 plus delta times clinic. I'm just, putting terms together, factoring out terms. Clinic is in there twice. So it's beta 2 plus delta times clinic. Well, if the clinic variable, which is my exposure variable, which is now in the model, has the coefficient beta 2 plus delta, and the clinic variable is a time-independent variable, and so now once I specify the value of this variable, I can get an odds ratio. I can get a hazard ratio. What's the hazard ratio? Well, it's e to the beta 2 plus delta. That's what the hazard ratio is. Can you see that? I mean, that's what it is. I mean, this is not that complicated, okay? Now, what if you're less than 365? What's G of t? It's 0, so what happens to this? Drops out. So all you have left is beta 2 clinic with beta 5 prison, but these variables don't involve exposure. So what's the hazard ratio in the model where G of t is 0? It's just e to the beta 2, okay? So what have I done here? What I've done is I've defined a model. I'm using what's called, this is an example of a Heaviside function. And what I've gotten is, from this model, I've got a hazard ratio that's different number depending upon whether you're before 1 year or after 1 year. It's a different number providing what? It's a different number providing what? Well, if delta was 0, it would be the same, right? If delta hat was 0 or delta was 0, if this thing wasn't significant, then I'm really saying the hazard ratios are the same before and after 1 year. So if I wanted to test whether I needed this term in the model, what would my test be? What would I be testing? I'd be testing the null hypothesis whether delta is equal to 0. How would I do that test? Either a wall test or a likelihood ratio test. If it was a likelihood ratio test, what two models would I be comparing to do that test? It would be this model with the model that doesn't have this term in it, this last term. And I'd be fitting these two models using pH reg, and I'd be getting 2 log likelihood statistics, and I'd be subtracting one from the other, and the degrees of freedom for that test would be what? 1, because I'm testing for one coefficient. So that's how I can test whether this is significant or not. And if it is significant and delta hat's non-zero, I'm getting 2 different hazard ratios. So this is a way I can actually do an analysis. Now, I'm making an assumption here. What assumption am I making? And it may not be correct. The assumption I'm making is that below 1 year, there's a constant hazard ratio, and after 1 year, there's a constant hazard ratio. Maybe that's not fair, because when we looked at the picture, it sort of looked like maybe after 1 year, it diverged. It wasn't constant. These are not that far apart, but maybe these get further and further apart. So maybe to say after 1 year, they're not the same. You know, but that's an assumption I'm making. But I can do some other assumptions, and we'll see this now. So here's the model. Okay, now here's another model. Here's another model. This is an alternative one I could use. Okay, now you're saying, oh, he's throwing a wrench into this, you know, and this is starting to get confusing. I want to out of here. I want to be, this is like one of the cartoons, one of the drawings, I want to be a taxi driver. You know, this is, you know. What's this model saying? Okay. Well, it's a different model. How do you know it's a different model? Well, it's got prison and dose like was in the previous one, but now what's going on here? What's going on here? It's got 2 time-dependent variables in the model, and it doesn't have clinic in the model by itself. In this case, clinic was in the model by itself, and then there was 1 time-dependent variable. Now, I don't have clinic in the model, but I have clinic times a G1 of t and a clinic times a G2 of t. It's a different model. But actually, it's not a different model, as we'll see, because let's look at what happens. Let's look at G1 and G2 of t, how they're defined. Now, they're sort of opposite ways. G1 of t is 1 if t is less than 365, 0 if t is greater than 365. Now, is that what G was here? No. G was G2. See this G2? That was the original G. See, G2 is 1 if t is greater than 365, and G is 1 if t is greater than 365. So I've got a G1, which is 1 if t is less than 365, 0 otherwise, and G2 is 1 if t is greater than 365. In this model, okay, I've got 2 product terms. Now, first thing you should look at when you look at this model is you say, I don't like this model. And why do you say that? Because it's not, it's not hierarchically well formulated because the clinic variable is not in the model by itself, right? You say, I don't like this model. You might say, this is not a legitimate model because I have two product terms and I don't have clinic in the model, okay, on its own, which would be required. Well, it turns out it doesn't really matter because this model turns out to be equivalent to this. You can have a model that's not hierarchically well formulated if it's equivalent to a model that is. Okay. Now, look at what happens here. For this model, what happens if t is less than 365? If time is less than 365, what's the value of G1? Value of G1. 1. What's the value of G2 if time is less than 365? 0. So what happens here? If t is less than 365, G1 of t is 1, right? Is that right? And G2 of t is 0, right? So what does the model look like? It has prison dose delta 1 times clinic times 1, and this term isn't there, right? Well, what's the hazard ratio when t is less than 365? It's e to the delta 1, right? Because that's the coefficient of the only variable in the model that involves clinic, okay? And what if t is greater than 365? Okay, well, then this one's 0 and this one's 1, okay? So this term drops out and you go e to the delta 2. Okay? So if you use this model and you look at less than 365 or greater than 365, what do you get? You get two different expressions for the hazard ratio. Are they the same or are they different? Well, they're different as long as delta 1 and delta 2 aren't the same, right? I mean, if delta 1 and delta 2 are two different parameters, which they are as far as this is one variable and this is another variable, if they're not equal to one another, you're getting two different hazard ratios, right? And you can see this by fitting the model and seeing what you get. But these are two. But it turns out this model is equivalent to the other model because whether you use this model or the other model, you're getting two different hazard ratios. As long as delta 1 and delta 2 are different, then you're going to get two different hazard ratios. So you can do either one of these two models. Which one do you want to do? Doesn't matter. Do whichever one you want. Okay? So let's see what happens now. Now, here's the code. I'm now showing you the code for how to do this. Okay? See where it says, and this is which one is this? This is the code to fit the extended Cox model data with two Heaviside functions. So this is the code for this one, for this example. Okay, so here we go. Code for this. Days times status. Look at the variables in the model. Prison dose, and then there's two other variables. It's called clinic T1 and clinic T2. See clinic T1 and clinic T2? They represent those two variables that I'm defining as clinic G1 of T and clinic G2 of T. But you notice that up to this point, I haven't defined them yet. And after this point, that's when I define them. I say clinic T1 is 0 if days is less than 365, then clinic T1 is clinic, otherwise it's 1. Okay, and clinic T2 is 0 if days, then otherwise clinic 2 is clinic. So by defining this, I'm actually doing something. I'm defining these two time-dependent variables after the model statement, which is required, which is what I have to do. If I did it before the model statement, everything is going to go to hell. Okay, I'm not going to get the right answer. Okay, I don't know whether it's going to go to hell, but in any case, you know. So that's what you do. That's how to do it for two Heaviside functions. That's what I'm showing you. Two Heaviside functions. Okay. Now, what did I say? What about if it's one Heaviside function? So how would you modify the SAS code below to fit an extended Cox model to the Attucks dataset containing only one Heaviside function? Well, what you do is you'd have prison dose, and you remember in the first model I had clinic by itself, and then I had only one time-dependent variable. Clinic times something, some function of time. And I don't know if you remember, but the second G2 of T was the original G of T. So that's why clinic T2, defined this way, is what you put in this model. So if I wanted to fit a model with one Heaviside function, this would be the code I'd use. And if I wanted to use two Heaviside functions without a clinic variable in the model, I'd use this. And both these models are going to give me the same answers, same results. Now let's see what results we get. That's what the next thing we have to do. Here are the results. Here are the results for the model where you get you have the two Heaviside functions in the model, clinic times G1, clinic times G2. See, it's got prison dose, clinic T1, clinic T2, and it's got the parameter estimates, the standard errors, the Wald chi-square, a p-value, risk ratio, which is really the hazard ratio, or it's e to the beta, and it's got confidence intervals around them. Now, look at these two coefficients. Why are they in bold? Why are they in bold? Because these are the two things. If you're running this model, you got to get coefficient, the delta 1 and delta 2, and go e to the delta 1 and e to the delta 2, and that gives you the two hazard ratios. So, if I go to this, e to the delta 1, this is delta 1, e to the 0.4596, you see what it is, 1.583? E to the 1.8282 is 6.223. And then I get a confidence interval around it, and I get some test of significance, a Wald test for this thing. Now, think about what you got here. Think about what the results say. Do these results correspond to what the data seem to say? Think about it. Does it correspond to what the data seem to say? What this says is below 1 year, there is a hazard ratio, and it's like 1.5 or 1.6. After 1 year, it's a lot bigger. Isn't that what the picture said? That's what the picture said. So I'm actually reflecting the picture by doing this analysis. Can you see that? And I'm also getting a confidence interval around it, and I'm also getting a test. In fact, you notice the test, this large one is significant, and this small one is not significant at the 5% level. So I have some arguments saying, well, early on, there's not much of a difference. There isn't a significant difference, at least at the 5% level, between the two clinics, but later there is. And now I've done an analysis, and I'm using an extended Cox model. You can see that's how you can do this, okay? And it's a nice example to illustrate. This is a good one to learn how it works, okay? Now there's more things you could do with this, and this is where time goes. Well, let's now look at this. This is the output. Now I've written it here and I've written it here. What I wrote here that I didn't have here is I also have minus 2 log L for this model, okay? So what would I do here? How could I use this information? I mean, what I could do is if I wanted to test the proportional hazardous assumption, I wanted to see if maybe those two hazard ratios really weren't different. I could compare this model with a model that didn't have these two time-dependent variables and only had clinic in there. That's what I could do, and I can get a likelihood ratio test. And do I have that? I'm not sure if I have it. I don't have it. But I could do that and come up with a test whether there's a significant difference. Okay. Well, let's go on. Let's look at the next thing. Next thing I'm going to show. Look at this next slide here. I don't know if you can see this. See what's on this slide. Look at this slide. This is a different slide. Believe it or not, it's a different slide. Here's the picture that we saw with the adjusted survival curves, but this is a different model. Can you see that where is it a different model? Where is it different than from the other two? I showed you two other models. Now you notice the first one I showed you had prison dose and clinic in there, and then it had a delta times, what did it have? Delta times clinic times G of T. That was the first model. That one. Delta times clinic times G of T. The clinic is now moved over to over there. But look at this model that's different now. This is delta times clinic, but it's not G of T. It's something called T of T. T of T. What on earth is T of T? Okay. Well, think about it. I've defined it here. T of T is 13579, depending on whether T is between 0 and 183. 3 if T is between 183 and 365, 5. What's going on? What have I done here? What's between 0 and 183? What's 183? half a year, right? So I'm saying let T of T be 1 if time is between the start of the study and half a year. Let T of T be 3 if we're talking about half a year to 1 year. Let it be 5 if you're going from 1 to 1.5 years. That's what you're doing here. Okay, that's what T of T is. Okay, it's really a step function. See that? Okay. Well, what does this model do that the other model that's different from the previous model? What do you think it's doing? Remember how I said that the other model had 2 hazard functions that were constant before and constant afterwards, but they were the same before and the same afterwards? What does this do? Here it is. Here it is. When T of T is 1, when T of T is 1, so you're between T is between 0 and 183. When T is between 0 and 183, T of T is 1. So what's the formula for the hazard ratio when T of T is 1? It's e to the what? Beta 2 plus delta, and this is a 1. It's e to the beta 2 plus delta. What if you're talking about between a half a year and 1 year? Then T of T is 3. So what happens here? What's the hazard ratio? It's e to the beta 2 plus what? 3 delta, right? Can you see that? And if it's between 1 year and a year and a half, it's e to the 5 delta, okay? And then 7 delta, and then 9 delta. What is this model doing that the other model didn't do? And let's assume when you fit it that delta, it turns out that delta is non-zero, is positive. Okay, what is this saying? Delta is positive. What's it saying? As you go from a half a year to 1 year to a year and a half to 2 years to 2.5 years, what happens? What happens to the hazard ratio? It increases, right? So if I wanted to allow myself to consider a diverging hazard ratio, I could even do this model. I mean, I can do things more complicated than the simpler thing, and I can see what I get. And if I do that, I can actually fit the model, get these estimates, and come up with the estimates. In fact, what I do is with the code, here's the code for this. I won't go over that. If I do that, this is what I get when I fit this model, clinic of T, T of T. And what I get for these hazard ratios, I'm just showing you the results. Look at the hazard ratios. 1.283, 2.237, 3.9. See what happens? I'm setting it up so they're increasing. So I'm allowing myself to reflect the fact the picture's different. If I want to do that, I can do it. And I can get confidence intervals around each one of these. So I can do that too. So you can do a lot of things with an extended Cox model that's even more complicated than otherwise. Now, one of the questions you might have, there's a logical question you'd have at this point. Well, there's all sorts of questions you'd have at this point. But the logical question is 13579, 13579. Why that? Why not 246810? Anybody think of that? What about 12345? Right? Why don't I do any one of those? Okay. What about 1, 7.5, 15.8, 23.2? What about that? Okay. Well, it turns out, now I'm going to show you something. This is the confidence interval. You get confidence intervals. Look at this. Look at this model. Different model. Can you see this is a different model? How is it different? Now T of T is 1, 2, 3, 4, 5. Now what's similar about, even though this model is different, what's similar about this model and the previous model? Even though one is 1, 3, 5, 7, 9, this is 1, 2, 3, 4, 5. If you're talking about these different values, the 5 different values, they're all equally distant from one another. 1, 2, 3, 4, 5 is 1 unit difference, and 1, 3, 5, 7, 9 is 2 units. They're all equally distant, even though there's a different unit that they're equally distant on. Okay? Now, if I do this, if I fit this model, I will wind up getting my coefficient. This didn't come out that easily, so I wrote the coefficient in here. The coefficient of this delta for this model is 0.5560, and these coefficients are different too because it's a different model, okay? But if I fit this model and I then say, okay, what do I get? If I plug in for this model what the beta 2 and the delta is for this model, and I compute the hazard ratio for 1, 2, 3, 4, 5, that is for half a year to the first half, the second half, a year and a half, the second year and a half, and then after 2 years. You see these numbers? 1.283. Have you seen these numbers before? And the answer is yes. Same numbers. Same numbers. So it turns out it didn't matter as long as everything was equally distant. Okay? I'm getting the same conclusion if I want to do diverging survival curves. That's sort of interesting. So, you know, if I wanted to allow for them not to be equally distant, then I could decide that I want to do that. They wouldn't be the same. Okay? So you can do this, you know. In fact, I even did this. And I'll let you look at this on a separate thing. I even did it. What's this? What's this? How is this model different? It's got clinic, and then it's got a variable clinic times t. What's t? It's not t of t, it's t. Time. Time 0, time 0.3, time 0.5, you know, time's changing. I fit this model, and I'll get estimates for the parameters in this model. Well, it turns out these are not equally distant exactly. This is a different, I've got a continuous variable in the model. Previously I had a categorical variable. But you can show when you fit this model, you almost get the same answers, but you don't get exactly the same answers. Almost get the same answers. And you're going to have to look at that. It's in the book. You know, you could think about that. But the message here is this is a way to do an extended Cox model. And it's kind of a neat example because you can see how you can do this thing. So you can see what you do. Now, it's not the last thing I'm going to do today because I got 4 more minutes. I want to do one other thing. I want to introduce something, but this is going to be discussed in the lab next week because I'm still not going to be here on Tuesday because we've got other things to do. I want to show you one other thing. One other thing. I'm going to start showing you one other thing. Where is it? Not there. What do I do here? This one. Whoop. Last thing I want to show you. I want to just show you this. Okay. The Stanford heart transplant study. Okay. Okay. Now this is a study where you wanted to consider people who got transplants. So see if you can find this. And then I'm going to show you a model. And I want you to just look at this model for a minute or two, because that's all the time I have. Stanford heart transplant. I actually have 3 models in here, but I want you to look at what I've called Model 3. Model 3. See if you can find this thing and just, you know, not have a nervous breakdown in the next 4 minutes, here, if you can. Okay. Now, here's a model. Is this an extended Cox model or a Cox proportional hazards model? Based on what I've written here, based on what you see, the way the model's written. Can you see it's an extended Cox model? Because I've got 3 variables that vary with time. See that? Okay. And there's a variable HT of T, which is heart transplant status. Okay. You remember when I introduced this thing on last Thursday? Today's Tuesday. Today's Thursday, on Tuesday. Well, here's a study where you had 103 patients, 65 of whom received transplants, 38 did not receive transplants. So there's 103 people in the study, okay? Now, if somebody received a transplant, okay, what happened with them? They were eligible to get a transplant, identified to be eligible. Then they had to wait until a donor came along. And if the donor came along and it matched with them, then they got the transplant. So here we have a variable whose value is 0 while they're waiting and changes to 1 when they get a transplant. What kind of a variable is that? Time dependent or time independent? It's 0 and then changes to 1 for a given person. Isn't that time dependent? Right? Okay. Now, what if somebody never gets a transplant? It's always 0, right? 0, 0 all the way through for the whole time they're followed. What if somebody gets a transplant, but it's a different person, so they got the transplant at a different time. They waited longer than the first person I mentioned. So it's 0 up to the time they got a transplant, but the zeros are longer. There's more zeros up to the time. So here's a model that has a variable that's reflecting sort of the key question of interest is whether if you get a transplant, do you survive longer? And the outcome is survival. And we wanted to control for their person's age at the time they got the transplant and what their score was when they matched the person's heart to the donor, their tissue mismatch score. Say that 15 times in a row. Okay, tissue mismatch score. Okay, and these are the main variable of interest is this one. Okay, so I'm just saying this is a model that involves time dependent, but particularly the main one of interest is HT of T. This is the main one of interest. Okay, and again, this is going to be discussed a little bit further in the lab if they decide they want to do it and we meet about it. I want them to do it. But this is a different variable. This is a different example because now the main variable of interest is an internal time-dependent variable. It's changing from one individual to another. How do you do this analysis? Well, you fit this model. You might get e to the beta 1. E to the beta 1 is the effect of the transplant variable, but it's a time-dependent variable. So how do you interpret that? So that's the thing you got to read about. Okay, so that's another example that's, a good example that's good to look at. And it's written up in the book and it's in these notes. So, done. Okay? Thank you. See you in a few weeks. Although I have office hours tomorrow to talk with anybody who wants to talk about their grades.